Welcome to the SAR channel, where sound and audio are demystified. It's easy to send analog signals from one device to another, but transferring audio digitally is much more complicated. Things like sampling rate, bit depth, control data, synchronization, and coding all need to match exactly for the connection to work. Most important of all is the data format. It matters more than the physical cable or connection type. Many digital audio formats have been created to let devices communicate, whether they're from the same company or different ones. With the right connection protocols, digital audio can be sent in real time over both short and long distances, using either open or proprietary systems. Fiber optic cables are great for this because they offer high bandwidth and work well over long distances. In many cases, though, audio files are sent in non-real-time transfers. In a studio, one of the most important connections is linking hardware devices so digital audio can pass between them in real time. A digital link is always better than an analog one because it keeps the signal pure, while analog adds quality loss from digital to analog and analog to digital conversions. To send digital data, you need both a data channel and a shared clock for synchronization. One cable can handle both, but when several devices are used, it's better to have a separate master clock. The connection also needs an audio format that both devices understand. Data usually travels one way from one device directly to another, running continuously without any back-and-forth communication. Multiple audio channels and extra data can be sent together in a serial stream. The data rate depends on the sample rate, bit depth, number of channels, extra data, and the coding method. If the receiving device is a recorder, it can record the incoming signal in real time, creating an exact digital copy of the original data. For coaxial cables, a key factor is how much the cable weakens, attenuates the signal at half the clock frequency. In general, the maximum usable cable length is where this attenuation reaches about 30 decibels. Professional cables can run 100 to 300 meters, while consumer cables may only work under 10 meters. Fiber optic cables, on the other hand, lose almost no quality over long distances. The SDIF-2 Sony Digital Interface Protocol is a single-channel digital connection used in some professional audio gear. A stereo setup uses two unbalanced BNC coaxial cables, one for each channel, and an extra coaxial cable for the word clock. This clock signal is a square wave at the sampling frequency shared by both channels, and any sampling rate can be used. In two-channel setups, SDIF-2 runs over a single-ended 75-ohm coaxial cable carrying a TTL-compatible signal. For the system to work correctly, all three cables must be the same length. Later, SDIF-3 and MADI were introduced to handle DSD direct stream digital audio used in SACD. SDIF-3 is designed for one channel of DSD per cable using 75-ohm unbalanced coaxial cables that send data as phase-modulated signals instead of raw DSD. MAC-DSD, multi-channel audio connection for DSD, supports professional multi-channel DSD use. It uses twisted pair Ethernet cables for direct point-to-point connections rather than networked ones. MAC-DSD can carry 24 DSD channels in both directions at once, along with 2.8 MHz DSD clock signals. Standard Cat5 cables are used. Hub connections have reversed pinouts to link inputs and outputs, while direct device-to-device links use crossover cables where both data pairs and clock lines are reversed. The Audio Engineering Society, AES, created a standard connection known as AES3 or AES-EBU for sending digital audio. It is a serial format that carries linearly coded digital audio data. This standard allows two channels of audio, along with extra non-audio information, to be transferred between professional devices. It's flexible enough to support special uses, multi-channel setups, and higher sampling rates. The current version updated the original 1985 version. The European Broadcasting Union, EBU, also adopted a nearly identical version of the format. AES3 defines a way to send two channels of sampled quantized audio through a single twisted pair cable. It can transmit signals up to about 100 meters without needing equalization, and even farther if equalization is used. The left and right channels are combined, multiplexed, in one stream, and the system includes its own clocking and synchronization. Because the format doesn't depend on a fixed sampling frequency, it can be used at any rate with the data speed changing accordingly. AES3 solves problems common in analog connections, such as polarity shifts, level differences, hum, noise, and high-frequency loss. It can also include data describing whether the signal is mono or stereo, if pre-emphasis is used, and what the sampling rate is. The AES3 standard uses several key terms. An audio sample is a sound signal that has been regularly sampled, converted into numbers, and stored using 2's complement digital format. A subframe contains one audio sample plus some extra data. Two subframes, one for each channel, are sent during each sampling period, subframe 1 and subframe 2. Together, they form a frame, and the frame rate matches the audio's sampling rate. In stereo, subframe 1 carries the left A channel, and subframe 2 carries the right B channel. For mono signals, data goes into subframe 1, but the two-channel structure is still maintained. A block is a set of channel status and optional user bits, collected over 192 samples, one per subframe. Each subframe starts with a preamble, which marks where the subframe and status block begin, while also helping synchronize and identify the channels. Each subframe contains 32 bits total, with up to 24 bits used for the actual audio data. The channel status bit in AES3 is used to send a block of data that is 192 bits long. This block is kept in sync by a special subframe preamble that appears once every 192 blocks. The AES3 standard defines 3 levels of channel status detail: minimum, standard, and enhanced. These levels determine how much information is sent and how the receiving devices interpret the data. In practice, an AES3 signal behaves much like a video signal. It uses a balanced differential output and a twisted pair cable, usually shielded for transmission. Cable runs up to 100 meters are common, and up to 500 meters are possible with adaptive equalization. Jitter tolerance is measured in unit intervals, UI, the smallest timing unit in the signal. Output jitter comes from both the device itself and its timing source. An AES3 transmitter should keep jitter below 0.025 unit intervals peak to peak when measured with a high-pass filter. A receiver must handle up to 0.25 unit intervals of jitter at frequencies above 8 kHz, with tolerance increasing to 10 unit intervals at frequencies below 200 Hz. The receiver should block both common mode noise and DC signals using transformers or capacitors. Having multiple receivers on one line can cause errors. The receiver's design must include a phase-locked loop, PLL, to reduce jitter and synchronize the incoming signal with a clean, low-jitter clock. AES3 connectors use XLR plugs, female for input and male for output, with pin 1 for ground and pins 2 and 3 carrying the signal. A simple multi-channel version of AES3 uses several two-channel connections. It can also connect digital microphones that perform AD conversion inside the mic itself, allowing control, power, and sync to be sent through the same line. The power feed can also carry remote control data. AES3 can transmit low bitrate data as well. By lowering the data rate, multiple channels can fit within a standard two-channel interface using the PCM data area for packing. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. The Multi-Channel Audio Digital Interface, MADI, expands the AES3 standard to handle many audio channels through a single connection. Defined by the AES10 standard, MADI can carry up to 64 channels of linear, serial digital audio at 48 kHz using one BNC-terminated coaxial cable up to 50 meters long with word lengths up to 24 bits. It remains fully compatible with AES3, transmitting all AES3 data bits such as validity, user, channel status, and parity. While AES3 needs 2 cables for every 2 audio channels, send and return, MADI can handle up to 64 channels using just 2 cables and a master sync signal. To save bandwidth, MADI uses NRZI coding instead of AES3's biphase mark coding. Unlike AES3, MADI is not self-clocking, it runs asynchronously, so the receiver must extract timing from the incoming signal to stay synchronized. For this, MADI includes a sync symbol in every frame, and all connected devices must share a master clock signal. The MADI format is based on AES3 subframes, sending all 64 channels serially within one sample period. Because of this shared design, MADI and AES3 data are directly compatible. MADI typically uses 75-ohm coaxial video cables with BNC connectors, carrying signals between 0.3 volts and 0.6 volts peak-to-peak and supporting data rates up to 100 megabits per second. The connection is point-to-point, so 2 cables are needed for send and return paths. For longer distances, fiber optic cables can be used, reaching up to 2 kilometers with an FDDI interface, or even farther with SONET systems. Since MADI works asynchronously, both transmitters and receivers use buffers to store and reclock data according to the shared master synchronization signal. The SPDIF, Sony Philips Digital Interface, protocol is made for consumer audio use. It is very similar to the professional AES3 standard, and sometimes devices from both systems can connect directly. However, this isn't advised because there are key differences in their electrical design and channel status data, which can cause compatibility issues. Devices that can handle both formats must convert the channel status information correctly. Unlike AES3, the consumer version doesn't use a balanced low-impedance line. Instead, it uses a single-ended 75-ohm coaxial cable carrying a 0.5-volt peak-to-peak signal over distances up to 10 meters. To maintain good signal quality, video-grade cables are recommended. Some consumer devices also use optical Toslink connectors with plastic fiber optic cables for distances under 15 meters. For longer runs, up to 1 kilometer, glass fiber cables with proper encoding and decoding circuits can be used. The Serial Copy Management System, SCMS, is built into many consumer audio recorders to control how many digital copies can be made. It allows users to make one digital copy of a copyrighted recording, but that copy cannot be duplicated again. Only first-generation copies are allowed. However, a recorder with SCMS can make as many digital copies as needed from an original source. SCMS does not affect analog recordings, but it can sometimes prevent users from recopying their own original work, even when it's legitimate. SCMS is included in consumer devices that use SPDIF connections, but not in professional AES3 equipment. The system checks whether the audio is copyrighted and whether it's an original or a copy. By law, all consumer recorders with SPDIF interfaces must include SCMS circuitry. The High-Definition Multimedia Interface, HDMI, is a digital connection that securely carries both high-quality video and multi-channel audio for TVs and computers. It delivers full bandwidth signals and is commonly used to link consumer devices like Blu-ray players, gaming consoles, and televisions. DisplayPort is another digital interface that also carries video and audio through a single cable. It serves as an open standard alternative to HDMI, often used for computers and monitors. The Musical Instrument Digital Interface MIDI is a standard used to connect electronic musical instruments, audio production gear, and music notation devices. MIDI is not a digital audio interface. It doesn't carry sound. Instead, it sends control, timing, and synchronization data that manage musical events and device settings. With MIDI, one instrument can control others, so each device doesn't need its own controller. Because MIDI only stores performance data, not sound, MIDI files are much smaller than audio files like WAV and can be downloaded or streamed quickly. However, the listener must have a MIDI synthesizer to convert the data into sound. MIDI is an asynchronous, one-way serial connection. It can also send system-exclusive sysx messages that contain data specific to certain devices, with sequences of any length. MIDI carries synchronization info too. Status bytes send beats, song pointers mark positions in a track, and MIDI timecode, MTC, sends SMPTE EBU time. MIDI show control, MSC, can run stage devices such as lights or effects. The general MIDI, GM standard, unifies basic settings like instrument sounds, used widely in games and online music. MIDI cables usually have 5-pin DIN connectors, though XLR types can also be used. The system uses twisted pair cables up to 50 feet long. Most devices have 3 ports: MIDI in to receive data, MIDI out to send data, and MIDI through to copy and pass the incoming data to another device. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. The AES11 defines how digital audio equipment in studios should stay synchronized. All connected devices need to follow the same timing signals so that samples are processed together. If timing is off, it can cause unwanted noise or clicks in the sound. A shared reference allows transmitters, receivers, and converters to work smoothly. Devices must match in both frequency and phase, and also stay synchronized with SMPTE time. Matching frequencies is easy. Both must use the same clock, so their bit periods are equal. But for phase synchronization, the bits must start at the same time. When one digital audio device connects to another, both must use the same sampling rate, and their bit timing must align. This is usually simple because most digital signals are self-clocking. The receiver extracts timing from the incoming signal. Sometimes a separate sync signal is used, but for basic setups, the receiver just locks onto the signal's sample rate. In larger systems with many devices, syncing frequency and phase becomes more complex. Each device may use a different timing system, creating small mismatches. To fix this, studios use a single master clock with high frequency stability and additional synchronizers that handle SMPTE timecode for full timing alignment. Although an AES3 line can distribute a stable clock, a dedicated word clock is preferred. The AES11 Digital Audio Reference Signal, DARS, was created for this purpose. It provides a highly stable clock to control jitter. DARS ensures that any audio sample can align with any other, or with video frames when combined with timecode. It uses the same electrical format and connectors as AES3, but only the preamble is used as the clock reference. A separate word clock cable runs from the master reference to each digital device in a star-shaped layout, using a distribution amplifier. Only a small buffer is needed to retime data at the receiver. If converters, AD or DA, use DARS instead of an internal clock, the timing accuracy of DARS must be very high, because any timing errors directly affect the audio quality. The AES18 defines how to format user data channels within the AES3 interface. This format is based on the packet-based HDLC communication protocol. It is used to send text and other types of message data, whether related or unrelated to the audio signal. The user data channel acts as a transparent data path with a constant data rate. Messages are sent as one or more packets, each containing the address of the intended receiver, so only the addressed device reads it. Packets can be added or removed as needed when data moves between devices. Common uses for the user data bits include sending messages like scripts, subtitles, editing details, copyright information, performer names, switching commands, and other notes. The AES-24 defines a way to control and monitor audio equipment using digital data networks. It works as a peer-to-peer system, meaning any device can send or receive control commands. The standard defines the structure and meaning of commands, but not how they are physically sent, making it usable with different types of networks. With AES-24, equipment from different brands can be managed through one common command format. Each AES-24 device has a unique address on the network, such as a port number. Devices can include processors, controllers, or other components, with or without control panels. Inside each device are hierarchical objects that handle tasks like adjusting volume, turning power on or off, or controlling indicator lights. Each object has its own unique address, allowing direct communication between them. Messages are sent from one object to another in a standard format and follow shared communication rules. When a message reaches its target, it performs the requested action, and if a reply is requested, a response is sent back confirming the result. The action can happen in any way through hardware circuits or digital processing. AES-24 subnetworks can link together into larger internetworks with bridges, hubs, or repeaters as long as all devices can communicate with one another. In a perfect digital world, all devices would use the same sampling rate, but in reality, many different rates exist. Devices usually cannot connect directly if their rates differ. Even recordings made at the same rate may be slightly asynchronous, differing by a few hertz, so they must be synchronized to a precise common rate. Jitter, timing variations in the clock, can also degrade a signal. Sometimes the sample rate can be changed easily, but often a dedicated sample rate converter is needed. A synchronous sample rate converter changes the rate using an integer ratio, keeping the output fixed relative to the input, which limits flexibility. An asynchronous sample rate converter, ASRC, can accept a changing input rate and produce a steady output rate, even if the input and output rates are unrelated. It can follow slow variations in input rate, solving many connection problems. Conceptually, sample rate conversion can be done by passing the digital signal through a DA converter, low-pass filtering it, and then using an AD converter at a new rate. In practice, this is done digitally using interpolation, inserting zeros to oversample and low-pass filtering, and decimation, removing samples and low-pass filtering to reach the desired output rate. The quality depends on the number of samples available to the decimation filter. By adjusting interpolation and decimation, almost any rate change is possible. This is usually done with polyphase digital filters, which oversample the input and compute the correct output sample amplitudes based on the input-output frequency ratio. The filtering process also reduces the effect of high-frequency jitter, smoothing the signal. An internal FIFO buffer stores input samples temporarily when the input rate changes dynamically, allowing output at a steady rate. This isolates the incoming jittered clock and aligns the audio with a precise, low jitter clock. A SRC makes sample rate conversion almost invisible to the user and solves many interface problems, including jitter. However, because these converters mathematically alter the data, it is better to use simple reclocking devices if only jitter correction is needed without changing the sample rate. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.